Hey, Charles.
Hey, Michael.
So, I get to lecture near you today.
Yes, you do. I can even see you.
This is crazy. I'm sort of don't have my regular pad. It makes me a little uncomfortable.
But you look very dashing in your nice blue suit.
Thanks. We're going to record some live action stuff today.
Mm.
All right. So, do you remember last time we were talking about Bayesian learning?
I do, because I led that.
Right. Good point. And so, one of the questions that I asked as a follow-up was these quantities, these probabilistic quantities that we're working with, is there anything that we need to know about how to represent and reason with them? And you said that I should look into it.
Yeah, because yeah, you should look into it.
So I did. So, and it's cool. And so I figured it would be fun to tell you about it.
Okay. Well, I look forward to it.
Thanks. And also I want to point out we're using a different color scheme today. Isn't that a nice blue?
It is a nice blue. It's sort of a relaxing blue, as opposed to that blue that we used before.
It's like cerulean.
Is it?
No.
It's more like periwinkle.
No, it's definitely not periwinkle.
Oh, you're right. It's not periwinkle.
Navy.
Periwinkle's no, it's too light to be navy.
All right. So, so good. So, right. So it turns out that there's this concept called Bayesian networks, which is this wonderful representation for representing and manipulating probabilistic quantities over complex spaces. And so it fits in really well with the stuff that you were talking about last time. All right, so to make this work, we're going to need to build on this idea of a joint distribution. It's not going to be obvious right away what this has to do with machine learning at all, but it's going to connect, so just bear with me for a little bit. All right, so to talk about this concept, what we're going to do is look at an example. And the example that I think might work, that would be nice and simple, is the notion of storm and lightning. So here's a little picture of storm and lightning. And what we're going to do is say, let's say on a random day at 2 p.m., you look outside. And what I want you to do is say what fraction of the time is each of these different possible combinations of things happening. So, for example, what's the probability that you look out and there's a storm and there's lightning at the same time? So what do you think?
On a random day?
Yeah, random day at 2 p.m. And it can be in Atlanta since that's what you're familiar with.
Is it summer? Because that happens more often in the summer.
Sure, let's say summer.
It's fairly high at 2 p.m. Let's say it happens a quarter of the time.
Wow, that's a rainy summer.
Mm-hmm.
All right. Now, that's not the only possibility, though. It could also be that there's a storm but no lightning.
Right, that happens more often at 2 p.m. in the summer in Atlanta. Let's say it's 0.4.
Wow. All right. Now, what's the probability that you look out the window and there's no storm but there is lightning?
Maybe 5%.
And what's the probability that you look out and there's, it's nice, clear, there's no storm, no lightning?
Coincidentally, I picked numbers that made it easier for me to subtract from 1, so it's 0.3.
Right, and so these are the only 4 possibilities we're saying, and they have to add up to 100%. And so it had to be 30 at this point. So it's actually more likely that there's a storm than not, according to what you said.
It's Atlanta in the summer at 2 p.m.
There you go. All right, so this is a joint distribution, and now we can actually ask various kinds of questions about this. Oh, you know what would be a good form for asking a question?
I don't know. I'm looking at you quizzically.
Nice. Using the fact that we're in the same place. We are going to do a quiz. You ready for a quiz?
Yes, I am.
Okay, here's what I'd like you to do. I'd like you to use these probabilities that we have written down here that constitute the joint distribution of when you look out, do you see a storm, do you see lightning? And use these numbers to answer some other questions that aren't directly in here, but you can figure it out. So the first one is to say, what's the probability when you look out the window at 2 p.m. in the summer in Atlanta that there's no storm? Okay? And then the second question is to say, what's the probability that if there's a storm, there's also lightning? Okay, so the probability of lightning given that there's a storm. And we've done some stuff with conditional probabilities, so these concepts should be familiar with you, but you should be able to connect it up with the numbers in the table. You ready?
I am ready.
Go. All right, let's hear it.
Okay, so here's the process that I went through. I was just going to talk this out. I haven't actually worked it all out in my head yet. So what's the probability that there isn't a storm? Well, the way you have this drawn, it actually makes it pretty easy to see. I can just look at the cases where storm is false. And it turns out there's 2 of them. And I can just add up those probabilities over there, and I get 0.05 plus 0.30, and that gives me 0.35.
That's great. Yes, so that's exactly what you did. So you went through, and now all that matters in the universe are the cases where they're not a storm, and that ended up being these 2 numbers. And you said, well, those are the 2 different cases that can happen. We'll just add their probabilities because they're non-overlapping, and you got 0.35. Great. Yeah. All right, what about the second question?
Okay, so that's probability that there is lightning in a world where there is a storm. So I'm going to do a very similar trick. I'm going to look at the cases where storm happens to be true, and conveniently they're the first 2 rows. And I have two cases. So we know the probability of there being a storm is 0.65, which is good because 0.65 and 0.35 add up to 1. But that's not the probability of there being lightning given there is a storm. So of those two cases, there's only one where lightning is happening when storm is happening, and that's 0.25. But 0.25 isn't enough because it's only 0.25 out of 0.65. So the correct answer would be 0.25 divided by 0.65, which is some number, 5/13.
Yeah, it's 5/13. And though I'd rather that people fill it in as a fraction.
Wait, that is a 5/13 is a fraction.
Good point. As a point something something, a decimal.
So 5/13 is obviously 0.4615. And there you go. Is that right?
Yes, that was perfect. Yeah, so it's usually when there's a storm, it's not lightning-y. It's less than half the time. That makes sense.
It does, because otherwise lightning would be happening all the time.
Well, when it's storming. It could be that it's very likely when it's storming.
It is likely when it's storming, but it wouldn't be happening every single time it's storming, because otherwise it would be lightning all the time when it's storming.
Right.
And often there's breaks between lightning. In fact, most of the time there's not lightning, at least outside my window at 2 p.m. in the summer.
All right, so that wasn't so bad. You're able to compute some probabilities from this joint distribution. So let's see what happens when we start talking about more variables, more propositions that could be true or false. What I did is I filled in thunder as another variable, and thunder can be true or false in each of these cases, and I wrote down what the probabilities could be from my experience in Atlanta in the summer. I was around over last summer and in 2004. So I'm an expert, obviously. So I'm able to estimate these probabilities to the nearest percent. Anyway, the point is that one of the things you should notice here is that each time we add one variable, what happens to the number of probabilities that we have to write down?
Well, in a world where it's binary, it goes up by 2.
A factor of 2, right? Not just 2 more, but like twice as many. And so if we have a complicated scenario that we want to be able to reason about, and it's got, I don't know, 100 variables, that's going to be a lot.
I can't even.
It's like 2 to the 100 is
that's not even a real number.
It's technically a real number, but it's an unimaginably large number.
There's only like 4 numbers: 1, 2, 3, many, and too many.
So it's going to be really inconvenient as we start adding more of these, and especially if we add variables like, remember the restaurant example that we worked on? We were doing decision trees.
Oh yeah, those were the days.
Then there was variables like food type, and what was the deal with food type?
It had lots of values that it could take on.
Yeah, like 5 or something like that.
Thai and American and Italian and.
Right, and so if we add a variable like that, it's going to multiply the number of probabilities that we need by 5. So this is going to get really big really fast. So wouldn't it be nice if we had a more convenient way of writing down this distribution?
Yeah, it would be nice.
So it turns out that we can factor it.
But I thought we already had a factor of 2.
Well, that was a joke, but it actually is pretty close to being the truth, which is the idea that instead of representing all, so in this case there's 8 numbers, instead of representing them as 8 numbers, we're going to represent it by 2 times 2 times 2. So we really are going to essentially factor it, putting things into pieces that we can recombine, smaller pieces that we can recombine into larger pieces. And it turns out that actually works out really well. All right, I'm going to hit you with a definition first.
Hit me.
So conditional independence is this idea that goes like this. We're going to say that some variable that makes up the joint distribution is conditionally independent of some other variable, y, given z, if it's the case that the probability distribution governing x, so the probabilities associated with the values in this variable x, is independent of the value of y given the value of z. If I tell you what z is, then you can figure out what the probability of x is without having to look at y. So that is, if it's the case that for all possible values, little x, little y, and little z, for the variables big X, big Y, and bz, if it's the case that the probability that big X, the random variable big X, takes on the value little x, given that big Y takes on the value little y, and big Z takes on the value little z, equals the probability that big X takes on the value x, given big Z takes on the value of z. If those are equal for all possible ways of filling in the values of the variables, then we say that x is conditionally independent of y given z, right? So you see we dropped y from the right-hand side of the probability expression. Okay, so it's sort of less things that we have to worry about if it's the case that we really didn't need it in the first place.
Fewer.
Fair enough.
So that's pretty similar to normal independence.
Okay, so what's normal independence?
So normal independence, we say the probability of x and y is equal to the probability of x times the probability of y.
That's right.
Which means if we think about the chain rule, we also know that the probability of x and y is equal to the probability of x given y times the probability of y. So that means that the probability of x given y is equal to the probability of x for all values of x and y.
So this is actually implying, so if it equals that, that means that px times py equals px given y times py. We cancel those, we get px equals, okay, so that's what you wanted to say.
Right. So since what independence means, right, is that the joint distribution between two variables is equal to the product of their marginals. And that's just, comes from basic probability theory. And so if you think about what that means from the chain rule point of view, it's like saying the probability of x given y is equal to the probability of x. So it looks just like the equation you wrote down for conditional independence.
Right. The only thing that we added is this notion that it might be the case that we don't have such a strong property as this, where it's always the case that you can write the probability of x given y just with the probability of x. But in the context of knowing some value z, it might be true. And that's what conditional independence gives us. As long as there is some z that we can stick in here that gives us that property, that's great. We can essentially ignore y when we're talking about the probability of x.
Okay, that's pretty cool. That seems more powerful or something.
Yeah, and in fact, remember you mentioned the word factoring. You can see here that we're writing down a probability as the product of two other things. We're factoring that probability distribution. That's what independence lets us do, and conditional independence lets us do it in more general circumstances. So let's apply this concept back to what we were just talking about before.
Okay.
So here's a quiz using this notion of conditional independence. So bear with me for a second because this is a little bit weird the way that I wrote it. But what I'd like you to do is find a truth setting for thunder and lightning. So like true, true, or true, false, or false, true, or false, false, such that the following thing holds true, that the probability that thunder takes on that value, given that lightning takes on the value that you give, and the storm is true, ends up equaling the probability that thunder takes on that value, given lightning takes on the value that you gave, and storm is false, right? So a setting here so that basically the value of storm doesn't matter.
So whatever I put in the upper left box has to be what I put in the lower left box, and whatever I put in the upper right box has to be what I put in the lower right box.
Right, and in fact, we're just not going to give you boxes for the other ones. We'll just give you the two top boxes and automatically fill in the bottom box.
Okay, that seems reasonable.
All right, so how are we going to figure this out?
By you letting them figure it out while I figure it out.
I think you should figure this out.
Okay, let's figure it out.
So it might not be obvious just looking at it blankly. So why don't we just throw in some values here? So for example, we can do this, which gets filled in both places. So the probability that thunder is true, given lightning is false, and storm is true, what is that number?
Well, so we just have to find the place in our little 8-row table where lightning is false and storm is true.
Where lightning is false and storm is true,
which is there.
Uh-huh.
And the probability that thunder is true is 0.04 divided by 0.4.
Oh, because we're asking about thunder. Right. What's the probability that thunder is true, given that the other two things, lightning is false and storm is true? So that's going to be divided by the 0.4. That's the setting that we're in.
Right. And 0.04 divided by 0.4 is 0.1.
Right. So maybe we'll get lucky and it'll work out the same with the other one. So where do we have to look for that one?
Well, now we have to look in the row where lightning is false and storm is false.
Okay, so it's down here.
And look at the case where thunder is true, and that's 0.03. And it's 0.03 divided by 0.3, which is also 0.1.
Woohoo! So that works as an answer. It turns out that, in fact, no matter what you type into these two boxes, it does, in fact, work. And what does that tell us?
Well, it tells us that it doesn't matter what the value of storm is. We can figure out the value of thunder by only looking at the value of lightning. So that is to say that the probability of thunder given lightning and storm is equal to the probability of thunder given lightning, or that we have conditionally independent variables.
Yes, that's right. Storm is conditionally independent of thunder given lightning.
Right. So if the probability of thunder given lightning and storm is equal to the probability of thunder given lightning, that means that thunder and storm are conditionally independent given lightning.
Or thunder is conditionally independent of storm given lightning.
Sure.
Very good. All right, so now what we're going to do next is say, okay, well, given that we have this nice property, and yeah, I worked a little bit to make sure that the numbers worked out. It doesn't always happen this way, but here we had some nice conditional independence, and what we're going to do next is look at a nice representation of that kind of information. So the concept of a belief network, sometimes also known as a Bayes net, sometimes also known as a Bayesian network, sometimes also known as a graphical model, and there's other names. But it's the same idea over and over again. And the idea is that what we're going to do is we're going to represent the conditional independence relationships between all the variables in the joint distribution graphically in terms of a little picture like this where there's nodes corresponding to all the variables and edges corresponding to dependencies that need to be explicitly represented. So the way that this works is what we can do is we can fill in the prior probability of storm, which we can get by just marginalizing out. So we've already done an exercise like this. So this is a number that you should be able to figure out. Then, because of this is also true that you can figure out what the probability of lightning is given storm and also given not storm. And these are numbers that you can just get by marginalizing out. Finally, the probability of thunder, normally you'd have to condition that on both storm and lightning. But as we already talked about, it's actually conditionally independent of storm given lightning. So all we need to figure out is the probability of thunder given lightning and the probability of thunder given not lightning. And once we have these, in this case, 5 numbers, that's enough to work out any probability we want in the joint just by multiplying corresponding components together. So what I'd like you to do is actually fill in these boxes as a quiz. And to help you out, we copied the numbers over from the previous slides so that you actually have the have the values that you need to fill in this table, because otherwise that would have been kind of mean. All right, Charles, can you work out these numbers?
I can. So the first one's pretty easy because we did that once when we were talking a couple of slides back.
We did.
We just look at the case where storm is set to be true. Those are those 2 mega rows there, and they're 0.25 and 0.4. We just add that up, and we get 0.65. Worth pointing out that since we know that S is 0.65, we know that not S is 0.35.
Good.
Okay. Even though that table really has 2 numbers in it, we only need one of them.
Right, yes. Very good point.
Because it's constrained by needing to add up to 1. And then we do something similar with lightning. We look at the cases where lightning is true and S is also true.
Yep, there's just one case like that.
There is only one case like that.
Right, but what we really want to know is what's the probability that lightning is true given that storm is true? So we need to think about both cases where storm is true and say, of these, what's the probability that that lightning is true?
And it's 0.25 over 0.65.
Right.
Which is 0.385 rounded up.
Okay. You're a cowboy.
Right, which means that the probability of not L given S is 1 minus that, or 0.615.
That's right.
Okay, so we do the same trick with probability of L given not S. So we find the case where lightning is true but storm is false, and that's 0.05, but we have to do it out of both cases where S is false, and so it's 0.05 divided by 0.05 divided by 0.35, which is 1/7, and 1/7 is approximately 0.143 rounded up. And so not L given not S is 0.857.
Nicely done.
I use subtraction in my head.
In your head, yeah.
Okay.
But it was like with carries and stuff. That was nice.
Yeah.
So, so let's see. And does these sorts of things make sense? So if it's not a storm, it's kind of unlikely that we'll see lightning.
Right.
If there is a storm, it's moderately common that we'll see lightning. Okay.
Right. That makes sense. Okay, good. So now we do the same trick again with thunder, except now instead of looking at L and S, we look at thunder and lightning. So we need to look at the case where thunder is true and lightning is true. So that would be that's all the cases where lightning is true, so it would be 0.2 divided by 0.25.
All right, and why are we just looking at the case where storm is true?
Actually, where are we doing it?
Because it's conditionally independent of storm, given
Doesn't
that
matter.
other information, so it doesn't matter which rows we look at. What matters is we look at a case where thunder and lightning are both true, and we compare that to thunder is false and lightning is true. So that's this number. Those add up to the 0.25. We get the 0.2 over the 0.25, which is 0.8.
Right.
So it's very likely to hear thunder if you see lightning.
That makes sense. And there's only a 20% chance that you don't hear thunder when you hear lightning.
If there's lightning, not thunder. Yep.
And so we do the same thing in the case where we have thunder and there's not lightning. So we find that row.
Okay, not lightning, and there is thunder. There's one.
Right. And we do the same trick we did before, and we get 0.04 over 0.4, which I think we did last time, actually, and we get 0.1.
We did. So if there's not lightning out, it's very unlikely to hear thunder.
Right.
All right, and just to drive this point home, that was great. Just to drive this point home, what if it was the case that it mattered what value storm had? How are we going to fill in this table?
Well, we'd have to look at a lot more rows.
Well, in particular, we couldn't draw this kind of belief network if that were the case, right? Because it wouldn't be conditionally independent. So we'd have to draw basically another edge here. And what that represents is that thunder, to work out what the probability of thunder is, you have to look at storm and lightning, all the joint combinations of those to make it work.
And that grows exponentially as you add more and more variables.
And that's right. And that's something that threw me when I started to look at this, because the picture looks a lot like a neural net, right? In a neural net, you've got these nodes, you've got arrows going into the nodes, and when you have a bunch of arrows going into the same node, you just end up like adding all those different influences together, weighted by what it has on the weight. This belief network representation is an entirely different animal. In particular, now what we're really saying is, to work out the value of this node, you need to know what's going on in all combinations of what the inputs are. And so, as you pointed out so astutely, that grows exponentially as you have more variables coming into the node, higher in degree.
So this is not just a network, it's a graph. And so we can talk about parents and children, right? So basically, the number of numbers you have to keep track of is exponential in your parents.
I mean, yes, though it's not exactly a tree. It doesn't have to be a tree. So the parent relationships are kind of weird. Like in particular, if you use parent terminology on this graph, what you're saying is that lightning has one parent, which is storm, and thunder has two parents, which are storm and lightning. So storm is its own grandfather and parent.
So let me ask you a quick question, Michael. So earlier on when you were describing this graph, I noticed you used the word dependencies. You said, we're going to capture the dependencies. So if you erase the red line between storm and thunder.
I'd be happy to.
So you erase that. Should I read this as storms cause lightning and lightning causes thunder?
You can do that, but you'd be wrong.
Oh, okay.
You can't infer that there is a causal relationship just because there's an arrow between them, right? So these arrows really are just telling us about the relationships between the probabilities and not necessarily anything about the physical processes that underlie them.
Okay, so let me make certain I understand. So what you're saying is it would be very natural to look at a belief network or a Bayesian net or a Bayes net or a graphical model and read the arrows as causes and therefore read them as talking about dependencies. But actually what's happening here is that these things represent conditional independencies. So it is not true that lightning is dependent on storm and thunder is depending on lightning, so much as it's the case that storm and thunder are conditionally independent given lightning.
That is a good point. I guess I never really realized that dependence, you use the word dependence, sometimes it means a physical dependence, like in the real world it's dependent. Here I'm just talking about statistical dependence. It's really just talking about the fact that we can derive numbers from other numbers and not that, things cause other things. So yeah, that's a really good point. It seems like that was an easy place to get slipped up.
Okay, cool.
All right, so now that we have a handle on this kind of representation, let's look at some things we can do with it. So here's an example of a Bayesian network with 5 variables, A, B, C, D, E. And let's pretend that each one has some set of possible values. It could be true, false, it could be red, green, blue, whatever it happens to be. And these arrows, again, tell us about our conditional dependence relationships. So how would we go about actually, say sampling from this distribution? So let's say that we wanted to just as an example, see what A, B, C, D, and E might look like in a randomly selected example from the distribution that this network represents. So it turns out what we can do is if we sample from A, now A is specified, has no incoming arrows, so it's not conditioned on anything in particular. So we can sample directly from A's distribution. We can do the same for B. And now C, if we want to sample from C, we need to make use of what values have already been selected for A and B, because C is conditioned on A and B. But we can sample from that distribution. Each value of A and B, each joint value of A and B, gives a distribution over C. And we do the same thing for D and the same thing for E. And when we're done, what we've sampled from is actually the probability distribution, the joint probability distribution. So does that seem like a useful thing to be able to do, Charles?
It does seem like a useful thing to be able to do.
Yeah. So here's just a quickie quiz. So just write a one-word description that says, well, in this sampling, you notice I went A, B, C, D, and E. What ordering do I need to do if I have a belief net like this, specified by this graphical structure with the arrows? If I want to be able to sample it, I need to do it in a particular order. Some orders are going to be problematic because we haven't actually, sampled the variables that it depends on. So what ordering should we select for A, B, C, D, E in general? What is the name for that, so that we can actually do this kind of sampling trick this way?
Okay.
All right, Charles, so what do you think the answer is here?
Actually, I don't know what you're looking for here.
Oh, okay. Well, so one thing that's true, we had to sample the variables from A to E, and that's alphabetical order. So do you think that's what I was looking for?
Maybe in this case, but I would think that that wouldn't be generally true.
True, right. So yeah, alphabetical is not what I was looking for. So there's it's a graph theoretic property that says we want to basically put the nodes in order so that you always put the things that have incoming links that haven't been visited yet after the ones where they have been visited.
Oh, so it is a lot like alphabetical or a lot like lexicographic, but it's topological,
There we go. Yeah, that was what I was looking for. So topological sort.
which makes perfect sense.
Right, and so this is a standard thing that you can do with a graph, and it's very quick to actually compute one of these. It does depend on a particular property, though.
Let's see. Topological only makes sense if you really can go from no parents to parents. So it cannot be cyclical. You can't have arrows that take you back. So E can't be a parent of A and also have A be one of its parents. So it must be acyclic.
Must be acyclic, right? And that's going to be true in these cases because we're always going to set it up so that in a Bayes net, the variable that each variable depends on other variables, but it ultimately has to bottom out. There can't be cyclic dependencies. So it is a directed acyclic graph.
So what would it mean if there were cycles?
I don't know. I don't know what to do with such a graph.
It just doesn't mean anything at all, I guess.
Yeah, I mean there is a family of undirected models.
Mm-hmm.
But we're talking only about the directed ones here. So the directed ones, yeah, it have to be acyclic for the probability distribution to be meaningful.
Well, that makes sense.
I'm sure we could make something up, but this is how it's done. We constrain ourselves to acyclic graphs.
Well, if a Bayesian network is supposed to capture conditional independencies, then if you had cycles, that's like saying there are none, right? I'm not even sure what that means.
I could make it mean something. So here we want the probability of A conditioned on probability of A. Well, maybe that's like probability of A, what A was one time step ago, or it could mean that that we're actually putting constraints on the joint assignment to all the variables. But yeah, it's not really. It doesn't really. It makes things more complicated, and that's not the model that is the typical one.
Okay, fair enough.
So another important thing that you can do with this representation is recover the joint distribution. Remember a couple slides ago we looked at the issue of how can we go from the joint distribution to specifying what the probabilities are, the conditional probability tables they're called, at each of these nodes. But we can actually go the other direction as well. We can go from the values in these conditional probability tables at each of the nodes to computing the probability of any combination, any joint combination of variables that we want. So it turns out it's really, really simple. We can just go and use these same ideas and say the joint probability for some assignment to the variables is equal to just the product of all the individual values. So the probability that that value of A would be taken times the probability that that value of B would be taken times the probability that that value of C would be taken conditioned on the values that were chosen for A and B. So it's just like in the sampling case.
Right, and that's much more compact a representation.
That's a good observation, yeah. So if these were Boolean variables, how many values would we need to specify for the joint distribution in the standard representation where you just assign a probability to everything?
Well, if I ignore the fact that there are some constraints we might be able to take advantage of, it would be 2 to the 5th because there are 5 variables.
Right. But here we've broken it down into smaller chunks. So the probability of A is just specified by a single number. Probability of B is specified by a single number. Probability of C is specified for a single number for each combination of A and B. That's 4 of them. This also requires 4 values, and this requires 4 values. So this is really what? It's like 2 to the 5th, minus 1, I guess, because if I tell you the first 31 values, the 32th value is just 1 minus the sum of all the others. So this is 14 numbers versus 31. So you're right, it is more compact. 31 is bigger.
Right, but let's imagine that all of the variables were in fact completely independent of one another. Then you would have 5. You'd only need 5 numbers, right? Because it would be the product of the unconditionals.
Yeah, which is what we'd get if we had kind of like just a set of weighted coins, that they're unrelated to each other, but each one has some probability of coming up heads. The probability of getting some particular combination, like A is heads and B is tails and C is heads and D is heads and E is heads, we could just break that down to the probability of the individual events.
Right. So then all of the, just like with the joint distribution where you have this exponential growth because you need to know everything, here you have the exponential growth that only depends upon the number of parents you have. If you have no parents, then it's constant. If you have parents, then it grows exponentially with the number of parents.
Good. Right. So the fewer parents, the more compact the distribution ends up being. Earlier I mentioned sampling, and I asked you whether that sounded useful, and you said it was. So let's do a little exercise. Why? Why? Why is that a useful thing? Why is it a good idea to be able to sample from a distribution?
Well, because it's one of the two things that distributions are for.
What does that mean?
Well, so why do you have a distribution? A distribution is so that given some value, you can tell me what's the probability of me seeing that value, which is kind of what it looks like when you have the probability function. But also, if you have a nice distribution, you can generate values according to that distribution.
Okay. That's a little bit circular in the sense that it didn't tell me why it was useful to generate them other than it's one of the things you can do.
Oh, you didn't ask me to actually make sense. But I mean, this is the thing that you use distributions for. Now, why would you want to do that?
Yeah.
So if a distribution represents kind of a process, it would be nice if I could duplicate that process, right? So I would have to be able to generate values in the right way, consistent with the distribution, in order to generate that process. So it's like flipping a coin. I want to flip a coin and find out whether I'm going to get heads or tails. It would be nice if I could do that in a way that's consistent with whatever the underlying bias of the coin is.
Okay, so yeah, so if this distribution represented something complex, we might, for whatever reason, need to simulate that world and act according to those probabilities. So yeah, that's a reasonable one. What else? What if I showed you this? If I took the distribution that we used for the lightning and thunder example, and what if you wanted to get a handle on it? How could we use sampling from the distribution to give you some insight into how the storms work?
Okay, so let's see. So I've got this representation of the joint distribution, but it's just a representation of the joint distribution. If I want to ask a question like, well, what's the chance that it's, let's say, storming outside if I've heard thunder? I could go through and back compute the reverse of the conditional probability tables, and I can do things like that. Or I could just generate a bunch of samples where I had thunder, and I can just see how often storm was also true. Does that make sense?
It does, though. I'm not going to use the words that you just used to write that down.
Okay.
I'm going to call that approximate inference. So the basic idea is that you would like to do some inference. You'd like to figure out what might be true of the world in different situations. And instead of doing some complex probability calculation, you're just going to imagine a bunch of possible worlds and see how often is it the case that whatever it is that you want to figure out is true. So yeah, that turns out to be a really good way to do it. In fact, sometimes I think that's a lot of what people are doing when we're making judgments in the world. We're just really, really good at this kind of sampling from past realities that are relevant, and we can make judgments based on that.
So how would you do that?
How would I do what?
How would you do this approximate inference?
We're going to get to that, but I wanted to.
Oh, okay, cool.
But there's one or two other things about sampling that I wanted to mention.
Okay.
Another thing that I could imagine using this for is this notion of visualization, which maybe is, I mean this in a broader way than it sounds. Not necessarily to actually see what the distribution is like, but to kind of get a feel for it. So I bet if I was to run that, if I was to draw a bunch of samples from the lightning thunder set, you would have a better feel for how likely different things are. Just you as a person might get a sense of how these things work. So you could imagine in a medical domain, a doctor who's thinking about prescribing a particular kind of drug for a particular kind of person, if the information about drug interactions and so forth was represented as a big belief net, it might be hard to look at it and know anything. But if you use that to generate a bunch of artificial patients, you might start to get to feel for, oh, you know what? These kinds of people tend to react badly in these kinds of circumstances.
That's still a kind of approximate inference, right? But
yeah, but it's right. That's right. So this is kind of in the machine sense, and this is kind of in the human sense.
Okay, I like that. So let's see if I understand it. So the nice thing about the storm, the thunder, and the lightning example is it has pedagogical value because it's easy for a student to look at that and go, okay, I understand what's going on here. One, because there's only 3 nodes and 2 arrows, and the other is because we think we understand how storms, thunder, and lightning work, right?
Yep.
Or most people do. So that makes a lot of sense. Of course, the downside of it is we think we understand it, and so it's hard to see why you would need to do samples. I mean, there's just a couple of probability distributions, and we kind of know what it means. But in the real world, there are perhaps hundreds and hundreds of variables with complicated relationships and conditional independencies that aren't necessarily intuitive just by looking at the graph. And so picking one conditional probability table and looking at it isn't going to tell you much. But by sampling, I get real examples that are concrete that as a human being I can understand without having to really grok all the 25 different conditional probability tables. Does that sound right? Is that what you're trying to say?
That's exactly right. Thanks.
Okay.
I want to draw your attention to this word here for a moment, this notion of approximate inference. Now, generally, we don't like approximations when we can do things exactly. So why are we not doing things exactly?
Because it's hard?
It's hard. That's exactly right. So, or even if it weren't hard, it may be in some cases faster. So, I'm not going to do it now, but I'd be happy if there's a groundswell of support amongst the students. I can go through the argument as to why this inference is hard. There's a nice little reduction to problems, NP-complete problems like satisfiability. But it turns out roughly that if you could do inference exactly on any belief net that you want, then you could solve very, very hard problems efficiently using that idea. So it's cute, but it's kind of takes us a little bit off our path, so I'm not going to get into that.
Okay, so sampling is useful, Michael, which I always suspected in my heart. And now we've got some good arguments for why it actually is.
So let's actually do some inferencing just to kind of get a feel for it. For certain kinds of networks, we actually can do things exactly, and we're going to look at one of those examples in just a moment. But it turns out it's helpful to remind ourselves of some rules of probability and inference that will help us do that. So here's just as kind of like a little cheat sheet for you. So marginalization is this idea that we can represent the probability of a value by summing over some other variable and looking at the joint probabilities of those. And if you have trouble remembering this one, this is how I like to think about it. If we're trying to figure out the probability of x, then one thing we can do is break the world up into, well, the cases where x and not y, plus places where x and y. So the probability of x it can be broken down into the probability of x when y is false plus the probability of x when y is true. So it's really simple in that sense, but it actually turns out to be a useful thing to be able to do, to marginalize out. The chain rule, we've used this a bunch of times, that the probability of x and y can be written as the probability of x times the probability of y given x. And that's important that we have the given x. If we drop that, what is that implying? Charles, go ahead.
Well, if you drop it, then that implies that they are completely independent of one another.
Right. That in the case where the variables are independent, you can just look at the product. In the general case, you actually have to look at the second one given the first one.
Right. And as I recall, the order on the left doesn't matter. So you have the probability of x times the probability of y given x, but you could have written the probability of y times the probability of x given y.
Yes. And actually, let's do a quick quiz.
Okay.
All right, so person who's adept at manipulating Bayes nets would note that this chain rule idea, this probability of x and y, can be written either as the probability of x times the probability of y given x, or as the probability of y times the probability of x given y, actually correspond to two different networks. So which of these two networks corresponds to the fact that the probability of x and y, the joint probability of x and y, can be written as the probability of y times the probability of x given y?
Go.
Did you get it?
Yeah, I did actually. So this one I think I understand completely. So we know that from the last discussion we had about how you would recover the joint, that what you're saying on the right of this equation, probability of y times the probability of x given y, means that the probability of y, the variable y, doesn't depend on anything. So between those two graphs, the one on the right is the one where you're saying that you don't need to know the value of any other variable in order to determine the probability of y.
Good.
So it has to be the one on the second one, and then just to make sure, if you look at the second product, the probability of x given y, or the second multican, is it multican?
Factor.
Factor? Let's say factor. The second factor, this says that, well, you determine the probability of x given the value of y, and there is an arrow from y to x. So the second one is in fact correct.
Yeah, so this is actually one way you could just read this network, is to say, what is this node x with an arrow coming into it? That is the probability of x, but the things pointing into it are exactly what's being given, what it's being conditioned on. So that's exactly right, the second one.
Right, and so this makes sense to me. This is why when you look at a network, a Bayesian network, it's very hard not to think of them as dependencies. Even though they're not dependencies, they're conditional independencies.
Well, the arrows are a form of dependence, but it's not a causal dependence necessarily. It's just the way that the probabilities are being decomposed. And the last of these three equations is just Bayes' rule, this time written correctly, where the denominator has to be the probability of x. And we've gone over this a couple times. I don't need to describe it again. But what I would like to just bring to your attention is that these three together turn out to be kind of our three musketeers in working out the probability of various kinds of events.
Excellent.
All right, so let's put some of these rules into play by actually doing some inference by hand. Ultimately, we're going to derive some algorithms that can do this, so you don't have to think about it so hard. But understanding those algorithms, it's helpful to have gone through an exercise where we actually use these ideas. So here's a setup. Let's imagine that we've got two boxes. One has 4 balls in it, and one has 5 balls in it. And we're going to choose one of those boxes uniformly at random. Either the box that we choose is equal to box 1 or the box that we choose is equal to box 2. And after that, we're going to draw at random, uniformly at random from what's inside the box, one of the balls. And let's say it turns out to be green. All right, so the first draw that we make, we have a green ball. We reach into that same box a second time, and the question is, what's the probability that that second ball will be blue, given that the first one we drew was green? So maybe to help point out how this is connected with Bayes-net inference, Charles, why don't you help me draw the Bayes-net that corresponds to this problem?
Okay, so if I think about it as a process, which now means I'm thinking about this as things causing the other, the first thing that you did in the process is you picked the box.
Good. All right, so let's say, so the first variable in the net is going to be the box variable.
Right, and then once I had the box variable I can now pick. The second thing in the process is I pick a ball. So in this case, you're calling it 1. So I make the first pick.
And do we need an arrow there?
Yeah, because you pick the box, and then that lets you pick which ball that you have. So which ball you pick, the color of the ball you pick, depends upon the box, so to speak.
Good. And so the probabilities here are going to be, it's going to look like this. All right, so the second variable here is what color ball you get when you do the first draw from the box. And we can represent this as a conditional probability table. So for box 1, it's 3/4 green, 1/4 yellow or orange, 0 blue. And for box 2, it's 2/5, 0, 3/5. And so that captures what happens on the first draw.
So for the second draw, well, clearly that sort of depends upon what you drew the first time, because you said we were drawing without replacement. So it definitely depends upon what you drew the first time, but also it still depends upon the box. Okay, so now we've got tables for a box, we've got tables for ball 1, and we need to know what ball 2 is going to be. Well, the value that ball 2 takes definitely depends upon whatever value ball 1 takes.
Sure.
But it also depends upon which box you're in. So you need an arrow from there as well. And what would be really nice is if we were in the storm, lightning, and thunder case, where if I knew that it was what ball 1 was, I would know what ball 2 was. But that's not true, because in a case, for example, when ball 1 is green, it doesn't tell me what ball 2 is unless I also know which box I'm in. So we have to draw the arrow from box to ball 2.
Indeed. Right. And so there's a lot of probabilities that we have to write down. But let's just write down a piece of that table. Let's say that the value of ball 2 depends on which box, and it depends on what ball 1 is, but let's just look at the piece of that table where ball 1 is green, because that's what we're ultimately going to need here. So now ball 2, in the case where we're drawing from box 1, the probability that's green. In the case where the first ball had been green, it leaves just 2 out of 3, right? And 1 out of 3 yellow and no blue. But on the other hand, had we drawn from box 2 first, and again, we had gotten green, now it's green 1/4, 0 yellow, and blue 3/4.
Right.
And we need the same thing for the other case where ball 1 is yellow and ball 1 is blue, but we're not going to need those numbers for this problem.
Right.
All right. So now that we've written it as a Bayes-net, is that helpful at all? So we haven't asked the question yet. So maybe it's time to ask the question, and then we can work on the answer.
Okay.
All right. The question is, what's the probability that the second draw is blue, given that the first draw had been green? Go. All right. So can you use this Bayes-net to help work things out?
Yeah, actually, it makes it a lot easier. I was thinking about how I would do this, and it would involve writing a whole lot of equations and doing a whole lot of stuff. But actually, just by writing out the Bayes-net, we ended up, and filling out these tables, we ended up doing that. So the bottom table basically tells me the probability of ball 2 being some color in a world where ball 1 is known to be green, because we just wrote down that part of the table, so we didn't have to do it for every other one. And, if I knew that I were in box 1, then the probability of it being blue in a world where ball 1 was green is in fact 0. And if I knew I were in box 2, then the probability of it being blue in where ball 1 is green and we're in box 2 is 3/4. So I only care about that last column.
All right.
And now I just have to choose the row or choose how to distribute the likelihood over the row. So all I really need to know is what's the probability of me being in box 1 or being in box 2.
All right, which we have in the table as well as a half.
Right. So that means the probability of it being ball 2 being blue in a world where ball 1 is green is just the probability of ball 2 being blue given that ball 1 is green. And we want to know the probability 2 is blue given that 1 is green, but when you look at the table and all we care about is that last column, all we really want to know is, well, we know the answer when we're in box 1, when box equals 1. It's 0. And we know the answer when box equals 2, it's 3/4. So if we were going to do a sample, for example, which you talked about earlier, we would just sample a bunch of times, and we would get 0 sometimes, and we would get 3/4 sometimes. And that would be great, except, of course, we want to compute this exactly. And we know how to compute it exactly because we actually know the distribution over how many times box would be equal to 1 and how many times box would be equal to 2. It would be a half in each case. So I think you've made this easier by giving us the table. So by actually writing out the Bayes net. So we want to know the probability that the second ball is blue given that the first ball was green. And that's just equal to the probability that the second ball is blue given that the first ball is green and we were in box 1. Because if we knew that, we knew we were in box 1 and the first ball we was green, it'd be really easy to compute the probability of the second ball being blue. It's right there in the table. It's 0.
Is this the way that you think it should be written?
Almost, but not quite. That would be the easy thing to do because we know that answer. We know the probability that box is equal to 1. It's just a half. But it's not just the probability that box is equal to 1. It's the probability that box is equal to 1 in a world where we knew the first thing we drew was green.
Gotcha.
And if we had that, then it would be easy to figure out the products there, to figure out 2 is blue in a world where the box 1 is green, box is equal to 1, and the first ball that we pulled was green. And then we would just add that to the probability that the second ball we drew was blue, given that the first ball that we drew was green, and we were in box 2, or we were drawing from box 2. And that would have to be weighted by the probability that box was 2 in a world where the first ball that we drew was green.
Good. Very good. And in fact, this rule that you kind of worked through follows just algebraically from 2 of the rules that we just talked about. It's the combination of the marginalization rule, which lets us introduce this box variable. But the way that we wrote it before, it was you have to and it in, but then we actually then applied the chain rule to split that into a conditional probability. So this is all valid at the moment. And are these quantities that we know?
Well, we certainly know the very first term in each of the 2 summands. Are they summands? let's say there's summands, and if they're not, we'll get nasty emails from people. The first part's probability second ball is blue given that the first one is green and we're in box 1, and the probability the second ball is blue given that the first one is green and we're in box 2. So that's easy. That's actually in the table.
That's easy. That's in the table. And it's 0 in this case, and 3/4 in this case?
Right. So it's 0 in the first case, and it's 3/4 in the second case, straight out of the table. And now all we have to do is figure out how often we're in box 1 and how often we're in box 2. And if you didn't think it through, you would just have the probability of box equals 1 and the probability of box equals 2. But we have to remember we're in a world where the first ball we picked was green. So now we just have to compute each of those terms. So how do we do that? So we want to know what the probability is that we're in box 1, given that we picked a green ball first. Well, that one's actually much easier to think about because Bayes' rule will allow us to express this in quantities where we do know the answer because we have the tables. So that would be the probability that the first ball is green, given that we were in box 1, times the probability that we're in box 1, divided by the probability that the first thing we picked is green. So the probability that we get a green ball if we pick box 1 is just, well, it's 3/4.
Yep. It's a different 3/4 than the other one, though.
Yeah, those 2 3/4 aren't the same 3/4. This way, because sometimes 2 3/4 are not the same 2 3/4. In this case, there are 3 green balls and 1 what we're pretending to call yellow because it's easier to write than orange ball, and so 3 of the 4 of them are green. So if we're in box 1, we close our eyes, we get 3 of those. So what's the probability that we're in box 1? Well, it's right there in the table. The Bayes net, it's 1/2. So now we just have to figure out, well, what's the probability that I would get a green ball the first time I picked one?
Right, and so one easy way to do that is we actually do this whole process again on box 2 and then just normalize. Or we could break this apart using the marginalization rule.
Yeah, which one do you want to do?
The first one, I think.
Okay, so figuring out the probability the first one is green isn't as easy as it looks. You can't just say, well, there are 5 green balls, but there's a total of 9 balls, and so it's 5/9, because those 9 balls aren't distributed equally on both sides of the boxes. So you still have to know which box that you're in some sense.
Right.
But we can kind of skip that step. Okay, so I like this. So what's the probability that the first ball is green given that we're in box 2? Well, it's just 2/5. Proof by looking at the screen. And what's the prior probability that we're in box 2? Well, it's just half because that was given to us from the table. And so we still don't know the prior probability of the first ball being green, but it turns out we don't have to because there are only 2 boxes, and so we can just normalize and the right thing will happen. So 3/4 times 1/2 is equal to 3/8, and 2/5 times 1/2 is equal to 2/10, or 1/5. And that's right. So 3/8 is also 15/40, and 1/5 is 8/40. Why do we do that? Because we want to be able to add them up and normalize. And so that means if you added those 2 together and put them in the denominator, that would give you 23/40. And so how much is 15/40 of 23/40? Well, it's 15 out of 23. And so without ever directly computing the probability that 1 equals green, we know that the probability of us being in box 1, given that the first ball pulled was green, is 15/23, which was a lot of work to do considering that we knew we were going to multiply it by 0, which meant none of this work mattered. But we did it because we love probability.
No,
so
it was kind of helpful because we needed to know how to normalize these 2 numbers.
Right. So it was useful. But, I mean, just the whole thing, we already kind of knew that was going to be 0.
But this one we didn't know.
Right. This one we didn't know. And so now we know that the other case is 8/23, and we're done. So 0 times 15 divided by 23 is 0, and 3/4 times 8/23 is 24/92.
Right. And there's a factor of 4 in both of those. So it's actually 6/23.
That's what I said.
Woohoo!
Wow.
Boy, it would be nice if we had an algorithm to do this for us.
Man, and the algorithm should not involve me.
All right, so what we'd like to do is work up to an algorithm that can actually do some of these inference steps instead of having to think it through each time de novo. So what I'm going to do is let's harken back to an example that we looked at before, which is about spam detection. Do you remember the spam example?
I do remember the spam example. That was way back in the boosting lecture, right?
Yes, I think you did that one.
I did. It was an excellent example.
There you go. So, but we didn't think about it in a Bayes net setting. It was in a classification setting, and we're trying to come up with a rule. But let's think about this as a Bayes net, where there's a bunch of different variables that can be true or false about any given email message. It can either be spam or not. It can contain the word Viagra or not. It can contain the word Prince or not. It maybe contains the word Udacity or not. Right? And so just as we think about these as these random variables, if we're trying to build a belief net or a Bayes net with these variables, we have to say kind of what's dependent on what in terms of representing the probabilities. So how do you think we should draw arrows to relate these different quantities to each other?
I think that the arrows should go down from spam to the other features of spam mail. And I'll tell you why. Because if I like this notion of generation that you talked about a little bit earlier, and it seems to me if you know you're in a spam mail or not, it sort of generates certain words. And as you've written this, these are like words. I mean, I know that in the spam example, these are, kind of stand-ins for features, but they're sort of features of spam mail.
Yeah, I think that's a really good way to think about it. So in some sense, what we're saying, if we draw the Bayesian net in this way, that any given email message has some probability of being spam. And given that it's spam, it has some probability of containing different sets of possible words.
Right.
So I would say that, well, what do you, let's see if we can actually fill in some of these values. So given that we have a spam message, how likely do you think it would be to contain a word like, well, let's say the word Viagra?
Fairly high.
So it might be something like 0.3. But a non-spam message might be, I don't know, like 0.001.
Right.
Something like that. So how about a word like Prince?
Well, I get a lot of email about Prince because I'm a Prince fan.
Yeah, I was thinking that. That's why I thought it would be an interesting example. So if in your spam messages, how likely is it for Prince to come up?
Fairly low.
So maybe like 0.2 because they're talking about Nigerian princes and whatnot. On the other hand, among your non-spam messages, how likely is it for Prince to come up, do you think?
Well, I get a lot of non-spam. So still relatively low, but not as low as 0.001.
All right, so let's say 0.1.
Okay.
That's a lot of Prince mail.
You can never have enough Prince mail.
Ow! All right, so in the messages that you have that are spam, how often does the word Udacity come up?
I guess it's pretty low.
I don't think I've ever seen a spam that mentions Udacity. All right, what about among your non-spam email?
Well, again, increasingly it's getting higher and higher, almost as much as I get Prince mail.
All right, so we'll call that 0.1 as well then.
Okay.
All right, so now we have, and what's the probability of spam versus not spam?
It's an interesting question. Probably have spam, it's pretty low. I'm going to say at this point, actually it's not that low. Actually at this point, it's probably half my mail.
Wow. All right, I'm going to say 0.4. All right, so this is now a Bayesian network structure that actually is, it's not exactly generating spam, but it is kind of capturing features of email messages as they come in. So we should be able to answer questions like, what's the probability that a given message is spam, given that the message has Viagra in it, but not Prince or Udacity? So how would we work this out?
Well, since it says naive Bayes, I think I'd use Bayes' rule.
That would be naive of you. All right, so now we've applied Bayes' rule. We've flipped things around. And why is this giving us an advantage? Well, for this kind of network structure, it actually is a huge advantage, right? Because we can actually break this first quantity up.
Oh, I do see that. Okay, so this is where those conditional independencies come into play. If I'm reading this network right, each one of those attribute values is conditionally independent of each other, given that you know the value of spam.
Excellent.
So then that means that the first quantity there is actually a product of each of those conditional probabilities.
Yeah, so this is a really convenient structure because it really just decomposes into all these separate helpful quantities. So in particular, we can actually derive this by applying the chain rule. But what we end up with is that this joint probability over these three variables decomposes into a product of three independent joint probabilities. The probability that it contains Viagra given that it's spam, which we have, that number is 0.3. The probability that Prince doesn't appear in it given that it's spam, and that is that it doesn't contain Prince given that it is spam, so that should be 0.8, because 1 minus the 0.2, and that it's not Udacity given that it's spam is going to be 1 minus this 0.0001, which should be 0.9999. All right, so this is the case when it is spam, and if it's not spam, we can do the same thing and get a product, and then we can normalize to get what the relative probabilities are between it being spam and not spam.
So then I'm a big fan of normalization, but of course this makes me think about, since it's sort of a classification problem, we only really care about knowing which one's more likely. We don't really care about the probability, right? Do we have to normalize?
Yeah, because we do care about the probability.
Oh, we do?
Yeah, because I asked, what is the probability of spam given these other quantities?
Oh, I see.
But you're right. So the observation that you're making is a really good one, which is that we can do probability calculations in this setting, and that's actually going to give us answers to classification problems. So we're going to connect this back to machine learning. But first, let's write a general form of this formula, because it seems a little bit specific. All right, so the general form of this, if we're trying to figure out the probability of some kind of a root node like this, when you have all these little bristly things coming down, you can think of it as the probability of a value given a bunch of attributes. And that's going to be equal to the product of the probability that each of those attributes would be generated by that underlying the label or the underlying class, times the prior probability of that V, and then we just normalize it by all the different possible values of V, this quantity across all the possible values of V. So, so this is one way of actually getting a very general kind of inference done. And there's, as you were pointing out, Charles, there's a really nice reason to think about things in this form, because it does let you do a kind of classification. So essentially, if you think of this top node as being the class, this is what was playing the role of V here, and these are all a bunch of attributes, then even if we have a way of generating attribute values from classes, what this lets us do is to go the other way, that we observe the attribute values and we can infer the class.
Nice. So what's the equation for that?
Right, so the maximum a posteriori class, if you're just trying to figure out what's the most likely class given the data that you've seen, you can just take an argmax over all the different possible values of that root node of its probability times the product of all the attribute values given that class. So this would actually let us, if you've been paying attention, we could, in this particular case, compute map spam, which is a palindrome.
Wow. That is spectacular.
You did not see that coming, did you?
No, I did not.
So this idea of naive Bayes, where you have a network that has a label producing or conditionally producing a bunch of attribute values, is just a really cool and powerful idea. So one of the issues is that even though inference in general is a very difficult problem, it's NP hard to work out what these probabilities are. When you have a naive Bayes structure, it's cheap. It's the formula that we had on the previous slide. The number of parameters that you need to write down, again, even if you have a very large number of variables, it's not exponential in the number of variables. It's just linear. There's 2 probabilities for each of the attributes and 1 probability for the class. We can actually estimate these probabilities. So far, we've only been talking about Bayes nets not in a learning setting, but in a setting where we just write down what all the numbers are. We can actually very easily estimate these parameters. How would we do that? Well, the easy way to do it is you count. When you're trying to estimate the probability of a particular attribute value given a class, it's really just in your labeled data, how often do you have an example that has that attribute value in that class, and then divide by the number of times that you have that class at all, and that gives you the conditional probability. So this is, and in the case of infinite data, this is actually going to give you exactly the right number. It also connects this notion of inference that we've been talking about with classification, which is mostly what this mini course has been about. So that's really great to have a connection. It actually allows us to do all kinds of interesting things, like instead of only generating what the labels are, we can actually generate what attributes are. We can do inference in any of these directions. And it turns out it's wildly successful empirically. So my understanding is that Google uses a tremendous amount of naive Bayes classification in what they do. If you have enough data, you can estimate these values really well, and naive Bayes is just remarkably good. So yeah, so it's like unclear why we'd even have any other algorithms, right, Charles?
Well, there's no free lunch, but I got to say, there's this, as a famous man once said, it works in practice, but does it work in theory? And I'm trying to figure out how this can possibly work. So I noticed it's called naive Bayes, and I think I know why now.
All right.
One is that it's naive, and in fact, painfully ridiculous to believe that the Bayesian net that you wrote up there in the upper right-hand corner represents the real world most of the time. Right?
I see. And why is that?
Well, because what that network says is that all of the attributes are conditionally independent given that you know the label. That just can't be true. We talked about this before where we were using Bayesian inference to derive sum of squared errors, that it makes a very strong assumption about where your errors come from and an even stronger assumption about where your errors don't come from. So you're not modeling any of the interrelationships between the different attributes, and that just doesn't seem right. So one question I have 2. I'm going to save the second one, though. One question I have is, how in the world can it possibly be the case that this works in practice?
That's a good question. It does. Moving on.
No, that's not satisfying.
No?
Well, how about I give it a guess? Okay.
All right.
Now that I've yelled at you, why don't I give it a guess? So I think it comes back to the conversation we had in the previous slide when I was saying, well, we don't care about probabilities. And you said we do care about probabilities because it was the question you asked, and that was fair. But once we're down to classification, the probabilities really don't matter, right? All that matters is that you get the right answer. So it's okay, I guess, if the probabilities you get are wrong, so long as they're sort of in the right direction, right? That you end up getting the right label as a result.
Yeah, that's a good point. That, in fact, even though we're introducing this idea in the context of Bayesian inference, it might actually not be so good at that, even if it is particularly good at classification.
Actually, I think I have a good example. So here, write this down. So let's imagine there are four. So actually, you can use the network that you have up there. Okay.
Good.
So let's say that the first attribute, I'm just going to call it A, and the second attribute, I'm going to call B. And let's say we're lucky, and our naive assumption is right, and they really are conditionally independent. But let's say the third attribute is actually just another way of writing down A. And the fourth attribute is just another way of writing down B. So clearly, there are interrelationships between the attributes, right? The third attribute is the first one. The fourth attribute is the second one. There's no way around that. And so you'd think naive Bayes would fail. But actually, looking at your equation right below there, where you're doing counting, I actually think it'll work just fine.
Why?
Because all you're really doing is double counting the sort of weight of attribute A, but you're also double counting the weight of attribute B, and they'll cancel each other out, and you'll get the right answer.
When you do the argmax. But
when you do the argmax.
You get bad probabilities. The probabilities end up being kind of squared of what they are supposed to be. But that's okay because the ordering is preserved.
Right, exactly. And so even if you were unlucky and the fourth attribute wasn't B, but it was something else C, it doesn't matter if you double count A so long as it still gives you the right label. And you can imagine that if you have weak interrelationships or you have enough attributes and so on that you would still get the right, yes, this is the correct label, even if you got the probabilities wildly wrong. Okay, so I'm willing to believe that could happen in practice.
Okay.
So, in fact, my guess is that naive Bayes believes its answer too much, but it doesn't matter if it happens to be right.
All right. And did you have other issues with it?
So the second problem I have actually boils down to that equation you wrote there. So it's really nice and neat that you can compute the probabilities of seeing an attribute given a value by just doing counting. But I don't have an infinite amount of data, right?
Not on a bad day, no.
No, or even on a good day, I usually don't have an infinite amount of data. So what if I'm unlucky enough that for some particular attribute value, I have never seen it paired with that label, V?
Right. So then that means this numerator will be 0.
Right.
So?
Well, that numerator is 0, but since the computation involves a product, by just having one attribute value that I've never seen before, I'm going to end up saying, well, the probability of that entire product of seeing that value given a set of attributes is also going to be 0. So one unseen attribute basically says it doesn't matter what else is going on, which seems a little weird, right? You think that if all the other attributes are screaming, yes, 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 it should be positive, that just because you haven't happened to have seen any examples of some other one single attribute, that shouldn't be enough to do veto.
Good point. So in fact, that's not what people often do. People will often, what they call, smooth the probabilities by essentially initializing the count so that nothing is 0. Everything has a tiny little non-zero value in it. And there's smarter and less smart ways of doing that. But no, you're absolutely right that zeroing out problem is a real thing, and you have to be a little bit careful.
Hey, I just had a thought. So if you have to do that, because if you don't do that, then you're believing your data too much. You're kind of overfitting.
Ooh, overfitting comes up again.
So okay. So bear with me on this, Michael. So if you're overfitting by believing the data and you're fixing it by being smooth, I usually spell it with a V, but whatever. If you fix it by being smooth, then you're making an assumption. There's a kind of inductive bias, right? You're saying that I go in with the assumption that that sort of all things are at least mildly possible.
Good.
Huh.
Yeah, that's right.
Okay. Naive Bayes is cool. You've convinced me.
Nice. So I was thinking of talking to you more about sampling, but it seems like it might work out best to just have some hands-on experience with it, so we're going to put those things on the homework. So given that, we're actually in a position now to kind of wrap up the whole Bayesian inference piece that we were talking about. So do you want to help remind me, Charles, what were the things that we covered?
Sure, I can help you with that. We covered Bayesian inference. I'm sorry. I'm punch drunk.
I'm going to choose not to pay attention to that. Instead, write Bayesian networks. We talked about the Bayesian network representation of joint probability distributions.
Right. And we did a lot of examples of how to actually do inference with networks. Exactly how do we compute probabilities of particular values. We mentioned sampling.
That's right.
And then we did naive Bayes.
Well, first we did say that in general, it's hard to do exact inference. It's actually hard to do even approximate inference.
Mm-hmm.
But we talked about a special case of Bayesian networks that was called naive Bayes, with the naive part being that we're assuming that attributes are independent of one another.
Condition on the label.
Right. And this was actually helping us make a link between all this Bayesian stuff, that Bayesian rabbit hole that we went down, and classification, which is the core machine learning topic that we've been spending a lot of time on.
So the other thing that I really liked about this, with this notion, this link to classification, Michael, is that when I was talking about Bayesian learning, right, what we ended up with at the end is this nice idea that we had a gold standard, right? We had a sort of way of talking about what the right hypothesis was and ultimately what the right classification was by computing these probabilities. And sometimes we couldn't do it because typically you can't actually do the for loop that requires you compute conditional probabilities of hypotheses given data over, say, an infinite number of hypotheses. But at least we kind of knew what the right thing was, and if we made right assumptions, we could do things like derive a sum of squared errors or various other things that you might do. And that was all very cool. But what you've done here when you do inference is, at least with the naive Bayes case, you've shown us a way that we can do classification using these things that actually is tractable and is the right thing to do under certain assumptions. So I really like that. And the other thing that I think that's worth mentioning is that not only does it link this Bayesian learning to classification, but it connects classification back to this general notion of Bayesian learning and Bayesian inference, where you don't have to worry about just figuring out the most likely label given a bunch of attributes, but because it's a Bayes network and you can compute anything from it, you could try to ask, well, what's the likelihood that I see some particular attribute or set of attributes given a label or given a subset of attributes, and on all those kinds of things that you could do with Bayesian learning. And so inference gives us this power to not just do classification, but to do a larger set of things beyond classification. I think that's kind of cool.
Cool. Yeah, well said. And another thing kind of in that same space is that it handles missing attributes really well. So whereas things like decision trees and so forth, if you give me an example that doesn't have one of the attribute values and you hit that part of the decision tree where you need to know that attribute value, you're stuck. Whereas in this naive Bayes setting, you can still do the probabilistic inference over the missing attributes because all the things are linked by probabilities.
Nice.
All right, so I think you'll get a much stronger handle of this when you go through the homework problems. But I think that's enough for Bayesian inference, and I think that actually wraps up classification and regression more generally.
Right, so we're done with supervised learning. Well, one's never done with supervised learning, but we're at least done with this part of the course.
Because there's always more to supervised learn.
That's right. And in particular, you'll get a nice example of this because you'll be taking an exam. And your input will be the exam, and then we'll give you a label back.
I guess that's one way to think about it.
Well, and then they'll get to generalize beyond that for the next time they take the exam.
Very good. All right. Well, thanks very much. This has been fun. Thanks, Charles.
This has been fun. I will see you on the second mini course.
All right.
Bye.